We can get started. So hey guys, this week we're going to be talking about interactive problems. So basically the idea behind interactive problems is you can ask queries to the judge and get responses, as opposed to with most problems where you get all your input at once and then you give the output. And your number of queries is usually limited, usually less than like a very small number, like usually less than like 20 or so, although some have different ones. And the query limit is usually very important for the problem. So it's very important to pay attention to that and how it relates to like all the constraints and things like that, which you guys will see as we get into a lot of these problems. So the best way to sort of learn how to do interactive problems is to just do a bunch of problems. So that's basically what we're going to do today. So the first problem, as kind of a warm-up, is, okay, so there's a hidden number between 1 and 10 to the 9, and you need to find it. And you can ask queries, basically you query a number, and the judge will tell you if your number is too big, too small, or equal to the hidden number. And we want to find x in at most 30 queries. So anyone have ideas on how to do this?
Yes. Yeah.
Do you want to elaborate on that?
Oh no, it's in the chat.
Oh, it's in the chat. Oh, I usually get a notification, but I didn't. Okay, yeah. So binary search. So what we can do is binary search for the value of x. So the queries that we do, you can use that as like your binary search check to see if like the number is too big, too small, or equal. And it turns out that we can do this in log base 2 of 10 to the 9, which is about 30 queries. Less than or equal to 30 queries, so we always have enough. So this is an example of like when the number of queries is very important, because you'll notice that we have 30 queries and the max value of x is about 2 to the 30. So that's kind of a hint towards the solution. So yeah, basically just binary search using the queries to check. And the code for that would look something like this. So just a couple like quick things about interactive problems in general, like for the implementation. It's usually nice to have some kind of like a query function where like you pass in whatever you want to print out and it returns back what the judge gives you. That just makes the code usually a lot cleaner and nicer to like deal with. Some other things, make sure you flush the output every time you print something. So like here, after we print the question mark A, we want to use endl instead of the new line character, because endl will also flush your output. And it's usually a good idea to flush the output at the end too when you're printing the answer, because if you have multiple test cases or something, then that could mess with you. So yeah, and then the rest of the code here is basically just a normal binary search where we have our L and our R. And in this case, we can just do a while 1 here, because we know we'll eventually break out of the loop. And then while we're in this loop, we find the middle element, we query the middle, and then if that's equal, then we can just print that and exit, which just quits the whole program. And then otherwise, if the element is too big, then we set R equal to m minus 1. And if it's too small, we can set L equal to m plus 1. So we're always going to shrink the range by at least 1. So this will always stop. It's not going to infinite loop. Okay.
I might want to tack on that there's something you can go a little bit further with having a query function. So what I would do personally actually is I would have a Boolean function called LEQ, right? So less than or equal to. And what I would really do inside there is that I actually check if it's equal. And if it's equal, I print out the answer immediately. And otherwise, if it gives me less than, I return true, otherwise I return false. So then my binary search becomes a lot simpler to write. Then it's just if query M, and then I directly set L and R. So that's another nice reduction you can do.
Yeah.
So the reason that works there is because whenever I do equals, like I pass, like I get back equals inside my LEQ function, I just exit 0. But that wouldn't work as nicely if like I had
Test
multiple test
cases.
cases or something.
Yeah. So there's like some flexibility in how you can do the query. But yeah, that would streamline this part a lot. Okay. Anything else on this? Okay. All right. So the next problem is guess the array, where this time you have a whole array hidden of size n, which is size like 3 up to say like 10 to the 5th or something. And you can ask queries of the form ij, and then the judge will give you ai plus aj. And you can ask up to n of these queries, and you want to recover the whole array. So I'll give you guys a couple minutes to think about this one. If you have any ideas, feel free to speak up in the chat or unmute or anything like that. Okay, yes, that's one thing you could do, is like ask all of the pairwise sums. So then, is there a solution with that? There might be.
I think that's enough information.
Yeah, I think it
to set up
is.
the linear system, but it's a much simpler way to think about this, I think.
Yeah. But yeah, there should be a way. I think the linear system might not be that bad if you do those queries. Yeah, I think you could do something with that. Yeah, there's also another way to do it.
Joe, chat.
Yeah, I see it. Yeah. Yeah, exactly. Yeah. So the thing we can notice is that first, let's solve the problem for n equals 3, right? Because that's one case we have to solve. So when n equals 3, you only have 3 queries, and there's only actually like 3 distinct queries you can do, right? Because you could also query like 2, 1 or 3, 1, but those are just going to give you the same information you already have. So there's only like 3 like meaningful queries you can give, which are 1, 2, 1, 3, and 2, 3. So then the question is, how do we solve the problem using just these 3 values? And yeah, like you guys said, what you can do is A1 is a half times A1 plus A2 plus A1 plus A3 minus A2 plus A3. Yeah, some similar thing in the chat with A2 here. And yeah, once you have that, then you can easily get A2 and A3 by just taking A1 plus A2 minus A1 and A1 plus A3 minus A1. Okay, so now we have the solution for n equals 3. And to solve n greater than 3, what we can do is use this solution for A1, A2, A3, which uses 3 queries. And then for all of our other indices, so for 4 up through n, we can query, say, 1i. And we already know what A1 is, and now we know what A1 plus AI is. So we can get AI as A1 plus AI minus A1. And in total, this is going to use 3 plus n minus 3 queries So we exactly hit our limit of n. And I think you might be able to do the pairwise thing, because that basically gives you like a cycle of n, like we were doing a cycle of 3 here. And I think you could maybe do something like get the sum of everything, and then like subtract out some pairs, and you'd be able to do something with that. Yeah, I think that does give you enough information. But this is probably going to be slightly easier to
I
code.
think some sort of alternating sums would work, right? And you left with only the starting and the ending one, and then or something like that.
Yeah, like if you like subtract out 1 and 2, and then subtract out 2 and 3, or wait, I don't know, it's something like that. I think that would be enough information.
You might have to do something with the parity of the n.
Yeah, that sounds right. Yeah. Okay. All right. Any questions on this problem?
Actually, I just wanted to throw out there that you're mentioning n equations and unknowns. There's actually some problems, they're kind of rare, but it happens in ICPC that you have n equations and you actually do full Gaussian elimination in n cube time. So that can be a thing. Just not here though, because you need linear. But yeah.
Yeah, that. I was gonna say it doesn't usually show up on code forces, but it did show up on one like somewhat recently. And then was it? I feel like it's been in ICPC a couple times, but I can't remember.
The circus problem from GNYR. The resistance graph? No, it's not circus.
Oh yeah, that one. Yeah.
There's also one recently in a 5-hour we did, right? It was like the last problem in the list. It was like we had a 3x3 matrix or something, and it just ended up being nice using Gaussian
well, I mean,
elimination.
I don't think we ever solved that one.
What do you think we didn't?
I don't think we did.
Oh, that sucks. But yeah, it was like helpful for that.
Yeah. Okay. Yeah, so that's one way you could do the pairwise thing. Although I'm not sure what the constraint on the n is. It might be too big. Yeah, okay. All right, so the next problem. Okay, you have an undirected tree with n vertices where the root is hidden. So we're trying to find the root. And you can ask floor n over 2 queries of the form uv, where you get the LCA of u and v. So basically, LCA of u and v is if you have two vertices, like here, if you have a and b, their least common ancestor is the lowest vertex in the tree relative to the root that is an ancestor of a and b. So like there's a path down from C to A and down from C to B. And C is the lowest vertex that satisfies that. The only other one would be R. So C is the LCA of A and B in this picture. So yeah, we have a floor n over 2 queries of that form, and we want to basically find R. Okay. So this is one where if you have any observations, like partial solutions, any sort of vague ideas, speak up, because there's kind of a couple observations you need before seeing the full solution. So one hint for this problem is to think about the leaves of the tree. So the vertices that are only connected to one other vertex. So like here in this one we have these 5 or these 6 vertices.
I feel like I already solved this problem, maybe, but the only observation I have for right now is that when I query two vertices, if I get a distinct vertex, then both vertices I've queried are no longer candidates for being the root. And if I get one of the two, then that still could be a candidate for the root. But at least the other one you can eliminate.
Yeah, so that's part of it.
I don't know what's going on with the leaves, though.
Okay. So what Adam is saying is, let's say you query A and B, and you get some vertex C, such that C does not equal A and C does not equal B. Then we know that A and B are both not the root, right? Because if say A was the root, then LCA of A and B for any B would just be A itself. But if it's C and that doesn't equal A, then we can basically throw out vertex A. And we can also throw out B because B does not equal C. But if the LCA is A, then that doesn't necessarily mean that A is the root. Because let's say A was this vertex here, and B was this. Then the LCA would be A, but A is not the root. Okay, so 1, 2, 2, 4, okay. Oh. Okay, so you sort of set up like another graph based on like the LCAs that you get and the pairs. Okay. So one I guess counterexample to that would be, let's say your graph was just these 4 vertices here, and then you queried like these 2 and these 2. So you would get like this vertex and this vertex, but you would sort of have no way of knowing which one of them was the root, because it would be like exactly the same situation if like we shifted this vertex here up to be the root. So Adam was on the right track when he was talking about like sort of trying to throw away vertices.
So I actually found this problem on Code Forces. I have I have 4 WA22s, 3 WA14s, 1 RTE1, a WA1, and RTE4.
Nice.
I think it's also in Java.
Did you get AC on it?
No,
Oh.
I don't know how to do this problem actually.
Well, I mean, if you got to like case 22, it's probably a bug in the code rather than the approach.
I think I'm asking too many queries or something. I think I remember doing this. I was doing
Okay.
something with the leaves and it just wasn't right or something. I don't know.
Okay. So yeah, what you were saying about like trying to like throw away the vertices is like very close. And again, the hint is to think about the leaves.
Think about your starting set, basically. You're supposed to, from what your approach.
Yeah.
Oh my god, you're given the tree. You're just not given the
yes,
root.
yes. You're given the tree.
I did not remember that. Okay. I don't know if other people understood that, but I was thinking about the wrong problem.
Yeah,
Okay.
I probably should have made that clear. You have all the edges in the tree. The only thing you don't have is which of your vertices is the root. Yes, yeah, I should have made that a lot clearer. Yeah, you can see the whole tree, but you don't know which one is the root. Yeah. That makes the problem significantly harder if you don't know the tree. Probably impossible. Yeah, so like because you know the tree, you, for example, you know where all the leaves are, which turns out to be very useful. Yeah, that's true.
You can say even stronger statement than just querying all pairs is a if you like whatever I don't know. If you also query all the leaves, you also get the root. Right? That's the other thing. Like the LCA of all you can't literally query that, but the LCA of all the leaves is also the root.
I think you can also do like a pairwise LCA of all the leaves, and that'll work. Like if you do a DFS and you order your leaves like that, and you query all the leaves that are adjacent to each other, then you get the root. But you can have more than floor n over 2 leaves. So that's also too many queries.
You also don't need to order it for that. You can just do a running, keep a running LCA, just like run through.
Oh, yeah, that's true. Yeah. No, not necessarily. Because if we added a vertex like up here, then your longest path would still be this one, or the one going to B. But that's not going to, the LCA of the endpoints would be this vertex, not whatever one's up here. Oh, right. All right, so I just like flashed some observations about leaves. So if you guys saw those, I guess you can use them for the solution. Actually, at this point, I think I can just show you guys the observations. This isn't the full solution. This is just some pieces we can use to get the solution. So first observation is we always have at least 2 leaves, as long as n is at least 2. And the other observation is if we take 2 leaves, then the LCA of A and B is A, if and only if the root is A. And same thing for B, because it's symmetric. So can we use these observations to solve the problem? And again, kind of going back to what Adam was talking about. So think about like, I guess don't really think about the tree as fixed. Think about like you can sort of change it, like throw out vertices or do things like that. Don't think of it as like a fixed thing, I guess. So I think pairs of leaves would be enough, or like if Keith said, you keep like a running LCA of the leaves, and let's say you have like L leaves, that would take L minus 1 steps, which could be more than n over 2. So yeah, that would work, but it would be too many queries.
This is very, very unrelated, but I just realized Google Meets has a raise hand button. I don't know, I just saw that.
Oh, wow. Thank you, Adam.
Wait, you can lower my hand?
Yeah.
That's not fair. I have my hand up. I had a feeling I was about to be removed from the meeting.
Oh. Oh, yes. Yeah, that works. And that's basically the solution. Except you can think about it a little bit simpler. Instead of querying like L over 2 pairs. Okay. Yeah, okay. So instead of thinking about querying like L over 2 pairs, you can think about it sort of one pair at a time. So pick any 2 arbitrary leaves and query their LCA. So if the answer is A or B, then we know that the root is A or B, right? Depending on which one it is. So then we can just print the root and exit. Otherwise, we know that A and B are both not the root, so we can remove them from the tree. And then by removing them, we're potentially creating new leaves. So we want to keep track of the degrees of all the vertices here and see when each vertex becomes a leaf as we keep pulling things off of the tree. And there's sort of 2 ways that it can end. Either we find the root in one of these A-B queries, or we do our floor n over 2 queries where n is odd, and there's only one vertex left. And in that case, that one remaining vertex would be the root. So for example, if this was the tree, what we could do is pick these as our initial A and B, and their LCA is this vertex here, which happens to be the root. But it's not A and it's not B, so we can remove them both from the tree. And note that removing A turns this vertex into a leaf. So if we keep track of the degrees of every vertex, and we decrement the degree of all its neighbors by 1 when we remove A, then we notice that this degree is now 1, so we turn it into a leaf. And removing B turns the degree of this vertex to 2, so we don't have to make it a leaf yet. But we keep track of that the degree is now 2. Okay, so now our tree looks like this, with this as a new leaf. And we can pick another 2 random leaves, like let's say these 2. And again, their LCA is R, which is not A or B, so we can remove them both from the tree. And then we pick another 2 leaves, and again, their LCA is not A or B. And now we pick these 2 leaves. And notice that the LCA of these 2 leaves is A, which means that A equals R. So now we can just print whatever number vertex A is and exit because we found the root. And notice that this is always going to take at most floor n over 2 steps, because every time you query a vertex, you're either going to immediately print either A or B or remove both of them. So we're splitting into completely disjoint pairs. So you only have at most floor n over 2 pairs. So yeah, that's how you can do it in n over 2 queries. Any questions on the solution? Yeah, it's really nice.
WA22 be like. I think my problem was just I was keeping track of the degrees of vertices wrong. I have no clue what was going on in my code. Also, I just shouldn't have used Java. It would be nice to have a map like from degree of the map, so map from the vertex to the degree, and just query all the edges around you. If any of them are 1 now, then.
Yeah, this is definitely going to piss off Thomas, but like, yeah, Java's very bad.
You don't.
I don't know. I don't know why I used Java for CP for like a year and a half. It did not make sense.
You don't need a map here for degree. You can just keep a degree of array of degree of each vertex, and if every time you decrement it, if it becomes 1, then you append it to your leaves array.
Yeah, I mean, you can. I think I did it with an array even in C++. I don't think you need a map.
Yeah.
Okay. Anything else on this one? Okay. So for the next problem, so a duck is walking on an n by n grid from the top left to the bottom right, moving only down and right. So like this is one possible path the duck could be going on. So before the duck starts walking, you can assign every square a value aij that's at most 2 to the 50. So you could, for example, give these values as your aij values. This is probably a very bad choice because you can probably have a lot of duplicate sums here. But yeah, this is like one possible choice you could give. And then after you give these values, you're given the sum of the aij values along the duck's path. So again, like if you had this grid and the duck took this path here, you would then be given a sum of 19, and you would have to recover this exact path. So yeah, like I said, this is probably a very bad choice. Yeah, this is a very bad choice because you can't distinguish between, say, this path and this path where we go through the other three and then do the rest, right? Because they're both going to have a sum of 19. So we basically want some way of assigning aij values to these squares such that every path has a unique value that we can easily recover. All right, questions on this? Okay. This is another one where it sort of builds on a lot of small observations. So if you guys see anything, feel free to speak up. And also for this one, really pay attention to the constraints because it's very important. Wait, I got a chat notification, but there's nothing in chat.
Adam raised a hand.
Oh. Are you going to say something or are you just raising your hand?
I was raising my hand.
Okay. I have a feeling this is going to be happening a lot. All right, so I think I'll give you guys the hint for this one, which is basically to think about it in terms of diagonals. Because we have, if you look at the diagonals from the top left to the bottom right, there's going to be at most 49 of them, right? Because n is at most 25. And you have like 2n minus 1 diagonals. So we have at most 49 of these. And we can use Aij values that are up to 2 to the 50. And another thing to notice is that along the path, the duck is going to travel on exactly 1 square per diagonal. So now the idea from here is like, how do we sort of use 1 bit per diagonal to solve the problem? Right, exactly. So that's how you can solve it. So what you do is along each diagonal, you make the values alternate between 2 to the like diagonal values. You can think about it as like sort of I plus j. So 2 to the I plus j and 0. And what this does is, so you know that you initially have to start in the top left square. And then you want to know in your next move, do you go right or down? So you can check this based on whether the first bit is set in your number, right? Because all of these values on these later diagonals, they can't affect the 2 to the 1 position of your number, because these are all like bigger multiples of 2. So the 2 to the 1 bit of your number is determined entirely by this orange diagonal here. So if the 2 to the 1 bit on your diagonal is set, then that means your first move is right, is down. Otherwise, that means your first move is right. And so now you'll notice that regardless of where we end up here, we're in a similar situation on the yellow diagonal. Because if we're here, then we have a choice of going to a 2 to the 2 or a 0. And if we're here, we also have a choice of going between a 2 to the 2 and a 0. And sort of at every square within this grid, like let's say we know we end up here after some sequence of moves, then we know we always have a choice between like 2 to the I plus j and 0. So by looking at which bits are set, we can determine whether to go right or down at every step. And there's no sort of nice correlation we can make. Like we can't always say, oh, if the bit is set, then you go right, otherwise you go down. Because, for example, the right from this square is the down from this square. But if you just look at your current position and what the Aij values directly down and to your right are, then you can solve it that way.
If you set it
Okay.
up slightly differently, couldn't you have like done some sort of thing? A parity 0 means you go means it's set versus parity 1 means it's unset or something like that.
Oh. Well, yeah, that's a very good point. So yeah, could we do this with like values less than 50? Or wait, that'd be like values less than 2. That's insane. I think that would work. Like if you replace all of these 2 to the whatevers with 1, and then you're just no, you can't. No,
That's not what I was saying.
no, yeah.
I was
I
just
wasn't
saying
thinking
use
about
the same values. I was just saying, it's so there is a nice correlation between like whether you go right or down. If you set this up just so all the parity 1 squares, right? The black squares in the checkerboard have their thing set for their respective diagonal, and the white squares in the checkerboard don't.
Okay. I mean, this is doing a similar thing, right? Where you just have to look at the parity of the row. But yeah, you could also
That's true.
wait. No, I don't think you can do the checkerboard because then I think these two would have to be colored the same color.
Oh yeah, I'm
Like
stupid.
you'd have to color the diagonals the same.
Yeah, my bad.
But yeah, this way you can check that basically just by checking the parity of which row you're on.
Got it.
Okay. All right. Any other questions on this? Okay. So now we can go into our last problem. So you have a mini golf course with 18 holes, where each hole has a windmill. And every night, some gophers attack, and you want to know how many gophers there are. And it's the same number every night. So you have 7 nights where you can do queries. And for each query, you assign every windmill a number of blades that's between 2 and 18. And you point the blade with index 0 down. And every night, each gopher picks a windmill to come out of and rotates that windmill's blades clockwise by 1 position. And at the end of the night, you know what direction blade 0 is pointing. So like, let's say you had a windmill with 4 blades like we have here. If one gopher came through, then blade 1 would be pointing down. If 2 came through, then blade 2 would be pointing down. If 3 came through, 3 would be pointing down. But then if 4 came through, 0 would be pointing down again. So basically for every windmill, you get the number of gophers that pass through it mod the number of blades. And yeah, you want to assign blades to each of your windmills separately. But there's no restrictions beyond that for what you can do. Like you could assign them all to be the same, or you could assign them all to be different values, or like a mix.
First observation, maybe I'm saying this too fast, but I haven't seen this.
Okay.
Is that there's exactly 7 primes less than or equal to 18. So probably something going on there. I also have another one, but I'll wait for a minute for saying it.
Okay. Yeah, so that's important.
You have seen this, by the way.
That's impossible. I have? Where?
And this was a code jam.
That doesn't mean I did it.
Yeah, I don't know.
There are code gems I skipped. I don't think I've seen this.
Yeah, so this is, I guess this is the first problem we've done today where primes are important. But primes tend to be important in a lot of interactive problems. So yeah, the fact that you have 7 primes under 18 matters.
Not kind of, not really. It's not super big deal. Like it's not primes.
No, I mean, it does, right? That's like, I don't know. I guess. I mean, it's like toward the end of the solution, but yeah, I don't know.
You registered for this code jam, but you didn't actually do any of the problems. I see.
I'm pretty sure I was asleep or something. I definitely remember there was one code jam where I registered and I just didn't wake up.
Fair enough.
So another thing to think about is how do we want to assign the blades to the windmills relative to each other? So like I was saying, you can have them all be the same. You can have them all be different. You can have any sort of mix of those. What would give you, I guess, the most information? So Adam, you said you had another observation?
Yeah, so it was that it can set everything to the same prime, and then if you add up all the remainders and mod it again by the prime, then you will get the like hidden number, like let's call it x, mod that prime, right?
Yeah, exactly. So
Uh,
yeah, so if we make them all have the same number of blades, yeah, if you add up all the counts and mod it, then you have the total mod B. So now the question is, can we do this? Like, is doing this for 7 different mods that are at most 18 enough information?
so yeah, this is where I was stuck on, and then I didn't actually know what this theorem does, but then I looked it up and it like does the thing. But I don't know if these guys know it. I didn't know it.
I mean, yeah, when I solved this problem, I didn't know it. I just kind of like picked 7 good ones. Yeah, exactly.
Yeah, it's your T, yeah.
But yeah, though, when I did it, I just like picked the 7 ones that like looked like they'd be good, and it just happened to work. So I don't know. I mean, I feel like you can kind of hand wave it a little bit, but the Chinese remainder theorem is like very helpful.
So I actually don't know how to do Chinese remainder theorem, so I guess I'm gonna learn now.
Yeah.
Cool.
So basically, Chinese remainder theorem is if you have like k coprime numbers, and you have some like hidden number x or whatever, and the mod values of x mod all of these mi values, then there's a unique solution less than the product of all the mods. So like if you know x mod 3 and x mod 5, then there's a unique solution for x less than 15, basically. And then after that, it's going to cycle, because if you have big M plus any value, then that's the same as, so like going back to the example we had, if you look at like 17 mod 3 and 17 mod 5, that's the same as if you subtract out 15. So that's the same as 2 mod 3 and 2 mod 5. But yeah, so as long as the values are less than the product, you have a unique solution. And we can use this using, for example, like these 7 numbers, and we can even increase this to 8.
16.
It doesn't really matter. Oh, 16. Yeah, we can increase it to 16.
Then,
Sorry, they all need to be coprime, right?
Yeah.
Okay.
Yeah, so all the mods need to be coprime, but you can make these like prime powers, and then that's still fine.
that's the thing earlier. If you just use the 7 primes below 18, that's not enough. You just use 7
right.
big coprime numbers.
Yeah. So you can bring this up to 16 and bring this up to 9, but that would be kind of overkill, because you know that the Gophers there's at most 10 to the 6 of them, and if you take the product of all these, it's more than 10 to the 6. So you have a unique solution. So then once you get your mod values, you can basically just check all of the possible answers from 0 up to 10 to the 6, and then you'll see which one works. And so Akif put this on the slides. So there's apparently an algorithm that lets you efficiently calculate the solution given all the mod values. I'm not sure how that works. But yeah, again, in this case, you could just loop over all of the possible values and see if it worked.
I'm not sure it works either, but it's on my template file, and it's like a really short function. So.
Yeah. Okay. All right. So questions on CRT or anything about the solution?
Just a comment that I'm finally like I knew the ring theory version of CRT, and I finally like know the normal version now. And it actually makes sense.
Yeah, that's nice. Okay. So that was all we had for. Oh wait, we also have implementation of this. So yeah, a key for this. I'm not entirely sure.
Oh yeah, I
What's
didn't realize
going
it was
on
Python.
here?
I forgot.
4 is not a
Yeah.
prime number.
I don't know what this Chinese remainder function does. I'm assuming that does the algorithm from the other slide. But yeah, basically, you read in. I'm assuming T is
It's
test cases.
Test cases, yeah.
Okay, yeah, and then you get N and M, and you get basically you print out your B value 18 times, and then you get in your Gopher mod values, and you add those up. Yeah, this is basically just doing what we were talking about. And then you do this magic Chinese remainder function at the bottom, which you can replace with a for loop, and then a check for all the mod values, because that'll be like 6 times 10 to the 6, which is will run in time.
I'm sorry, Chinese remainder is not like built in, is it?
No,
Right? It's just like adding above.
wait, there's no way that's built in, right?
It's not. It's not. I just
Okay.
copied and pasted Stack Overflow. I think.
Okay. Yeah. All right. All right. So yeah, the slides are in the info channel as always, and we will have the recording up soon. And on Wednesday, we're going to do a contest with a bunch of interactive problems. So hope to see you guys there.